자, 오늘은 챕터 10, 빔 theory에서 나가겠습니다. 챕터 9의 그 thin wall shaft는 이 흐름에 잠깐 스킵하도록 하고 today we're gonna study about the beam theory in chapter 10. This is a continuation of a last chapter which we studied about the torsion theory. Okay. And as I emphasize many times, in solid mechanics, the beam theory is the most important theory, and one of the reasons for why the beam theory is so important is that the beam is very widely used in real structures. That's the first reason. And the second reason is that when the structures and beam is subject to a bending moment, the stress can be very severe compared to other structures such as the bar or a shaft. So simply the beams are can be defined. Beams is defined a member whose length is the relatively long in compared with its cross-sectional dimensions, and loaded with a transverse load, which is the transverse load is like that. So this is the beam structures, and the load are vertically applied, and mainly a bending moment like that, and then this structure is called the beam structures. Again, the difference between bar and shaft and beams is not determined by the shape, mainly determined by the load. Okay, the bar and shaft and beam is the bar is the under axial load tensions, mainly even under compression as well. The shaft is the is a torsions like that, and beam is something like bending moment. And here it indicates the vertical load which will produce in cross sections certain bending moments. And again, as I mentioned, the most common types of a structural member is the beam, and beam can be found in many geometry, size and shapes and orientations. Okay. And beam deformations, first we need to observe the beam deformations. Again, the flow is very similar to what we have done in the torsion theory. Remember, we observed the deformation first, and then we defined the strain in terms of displacement, and we use the stress-strain relations. And once we have a stress, we define the torque in terms of a stress, which is equilibrium. And that's the flow chart. You remember that A+1 flow chart, and in the center line, we start from the bottom to top. It's very similar to that case. At the beam, we do the same thing. So we want to observe the deformations. Well, first, let's say the beam was just a straight beam like that, and then subject to a bending moment like that. Okay, this is a moment we apply to a beam, and the beam will simply bend like that, and then pay attention to top and bottom surface, and And it's clear that the top surface will be under compression. Top surface will be a compression in this case, and bottom surface is simply subject to a tension. So this will be the tension, and this will be the compression. So real shape will be like that. As you can see here, this was the original length, and as you can see here, this one become shorter, and the bottom one is under tension, and under tension, this one gets longer. And from this, we can conclude that there is a certain line, okay, a certain line where the strain is zero. The strain is zero. I use the epsilon xx because this one is the coordinate x. And this is a very simple observation. And what's happening when these structures under bending. Okay, so the point clear, you remember, is that the top surface needs to will be under compression, and the bottom surface will be under tension. And very importantly, the cross sections. Okay, cross section. This was the cross section. What this can be the cross section. Cross section remains the plane even after bending, which means that this section will remain the plane after bending. So this one does not bend like that. Does not bend like that. All the straight, the plane remains the plane. Okay, plane remains plane, and shear deformation is negligible. Actually, this observation and that observation is the same thing. Shear deformation, if we have a shear deformation, this may have a curved deformation. But since we don't have a shear deformation, and the cross section remain plane. And also another important observation is the cross section remains planar and vertical to the longitudinal axis, which means that we originally had this line. This is a longitudinal line, and the vertical section. This is the vertical sections, and these vertical sections remains as still vertical section. Vertical toward this longitudinal line. So this is the longitudinal line, and like that. And after deformation, this vertical line still is a vertical line. So now I want to express this deformation of observation in more mathematical patterns. So next slide is about the strains using some mathematical formula. Okay, here this is the before deformation, one part of the sections and under a bending load, and so we can say that on the right-hand side is subject to a bending moment. Also, left-hand side is subject to a bending moment M. Now, here is the x-axis, which means that in some position here, this line is the y equal 0. That this position is very important, which is called a neutral axis. We will decide where this axis exists. So say we have a certain positions y, okay, and from this y equals 0, let's say this is the line A, B, and after bending, this will deform like that, as you can see here, A plus and B, A plus, A prime and B prime. And the cross section, as we observed before, the cross section remains a straight. And so from this, we can see that there is a center of curvature, and this one, this line now is simply make a radius of curvature r. Okay, we assume that this line is the make a circle with the radius of r, and then this one make a delta t, delta theta, and then this a prime and b prime, the position was the y, and so this radius from 0 to this line, the radius will be y minus r minus y, because this one is the y, and that from here to there is the r. Okay, so from here, the center line to this position is simply r minus y. Okay, that is what we need to have to drive this train in terms of a y. Now, let's define the epsilon x. What is the epsilon x of this AB line? And simply the strain is the original length. Original length was the dx. And after deformation, we have A prime and B prime. And before deformation is AB. And so the AB is the original length before deformation, and this is the after deformation. Now, how to calculate this A prime, B prime? And this is the length after deformations. And to calculate this one, simply we have a radius r minus y. So this is the after deformation r minus y, and so this length will be simply this is a d theta, and then times this radius. So the r minus y is the radius, and this is a d theta. That is the length of A prime and B prime. And very importantly, the original length was the AB, and AB was a dx. But dx, as you can see here, this line does not change, does not change. So AB is the same as this line, the lengthwise, and this length is the same as this one. And this length, okay, this length now can be represented r, okay, here is the radius, r times the d theta. So the, again, this length is the r times the d theta, and that length is the same as that one, and that length is the same as that. So the before deformation, we can say that r minus d theta. So r minus d theta, and now this term and that term will disappear, and d theta disappear. And so this one is a very simple but very important equations. Epsilon x, x directional strain is simply proportional to y and divided by r. Okay, and there is a minus there. What it means is that if the positive y, there this part is the under compressions, and this is the net minus, then this will be the positive strain. And simply also 1 over r, we say the curvature k. So if we have a more bending, and then we will have a more the r will be m. If m is increased, r will be a decrease, and curvature will simply increase. So m is a proportional to a curvature. That's the main reason why we want to define the curvature rather than r. But r geometrically is very clear and very important in defining the strain. And also this r d theta, okay, r d theta is the simply dx. That was the one we observed, and so k was simply 1 over r. So from these definitions, 1 over r is simply d theta. Okay, 1 over r is d theta over dx. D theta over dx. What is d theta over dx? D theta is this one. Well, we can put it in this way. This is the d theta. Original one was the like that, and this one was the say dx. And this one is simply rotate this much, and the amount of a rotation we can call d theta. So d theta over dx, that is the rotations. Okay, so the d theta over dx is the rate of the angle change. Okay, this one gradually, this one we change this way, this one we change this way, this one we change it that way, and this one we change it that way. So this one is a theta, the cross section is rotating and gradually. So d theta dx is the deformation. So epsilon x, now this is the curvature, and curvature can be written as a dx d theta over dx. That's the rate of the angle, the cross section rotations. Okay, this is rotations, and actually this one and that is the same thing. We want to show how this cross section rotate with respect to this cross section. We can also say that these cross sections rotate with respect to this one. It's basically the same thing. So anyhow, this one we observe that epsilon x is a proportional to y, and this is a constant dx, d theta dx, the rate of the rotations, and that is the strain definitions. Basically, this epsilon x has a relation with the displacement, and this displacement we can say ux. Ux is the here. The ux is this way, and that is moved to here. And geometrical is a little bit complicated, but ux can be said is a proportional to x. Okay, proportional to x and proportional to y, and minus y, and the rate will be a d theta dx. Actually, this is the displacement observation we made, and this one can be written as like that. The geometrical is a little bit difficult, and this time the starting with the strain is a little more easier than strain, but in terms of displacement, this field can be written as ux. Okay, ux directional, as you can see here. For example, take a look at this line and here, and move, and actually this move. This one is moved, and this one moved, x moved, and this one x moved, and this one x moved. So it's simply proportional to x and proportional to y, which we observed, and the rate, the constant is the d theta dx. And this one is equivalent to this because epsilon x is simply ux and derivative x. So as you can see here, these are identical relations. Okay, this is the strain in terms of displacement. Okay, now is the stress-strain relations. Say we have a strain. How to calculate the stress? Well, simply we have a tensile stress and a tensile strain. Simple stress-strain relations. We don't have any other stresses. Others is all zero, except that this is x and this is the y. Only sigma x is a non-zero, and actually we can see any portion, and here this is like that, and this much, right, and this much, and we can take any part here, and this part is subject to a sigma x. So no matter which part we consider, and this part and that part, each part always the subject to a sigma x only. So sigma x is simply is well known, stiffness times epsilon x, and now we have epsilon x, which is like that, y over r, and which is also a y d theta dx, and we this is a beam, and so beam means that, let's say this is the h, and h and b. What is the b? Actually, I didn't draw. If we draw it, this is a three-dimensional case. This will be something like that, and something like that. So this will be the b, and this will be the length. So as long as b and h is less than l, and then this sigma y and sigma z is much less than sigma x. So we can assume that sigma y and sigma z equals 0. Anyhow, this is a simple stress-strain relations. That is the next. That is the step after strain, and the last step is the equilibrium, moment equilibrium, cross sections. Okay, what it means is that these cross sections, back to here, since the strain is the linear, okay, strain is the minus y over r, linear, like that, and we simply multiply the material property E, then of course the stress will be also linear. So this stress sigma x will be linear like that, and this cross section actually subject to a bending moment m. So we want to relate this moment m and this sigma x. So by definition, a moment is simply sigma x times dA. If let's take a look at this, and we consider this is the sigma x, and this is the cross sections. Again, if I draw this one three-dimensional, then this will be something like that, right? So this one is the cross sections, and this is the a dA, and the sigma x is applied. So sigma xx and dA, this will give us the force, and then the height will be the y, and then we need to multiply y, and then simply integrate over the cross section, which will give us the total moment m. So this is the definition of m, and that is the equilibrium between m, which we applied externally, and this is the sigma xx, which generate internally. So this is the equilibrium. And now this sigma xx is simply E times epsilon xx, and epsilon xx is simply minus y over r, and we put it here, and this is the a stress here, and then this one, and put it here. Well, this one is one step further, and this one, so y and dx d theta. So there is a y here, and there is a y here. So y square and Young's modulus E and d theta dx, and then integration. See, over the integration over the cross sections, this d theta dx is a constant. So out of the integration, and Young's modulus E is the also constant out of integrations. And then what it left in the integration is the integration y square dA. That is the one we call bending moment of inertia. This is the moment of inertia we call IZZ. And so this one, dx, d theta dx, and Young's modulus, and this is a moment of inertia. So what was unknown is this dx d theta, which is constant but was unknown. So the rate of the angle change under bending moment d theta dx was now simply moment divided by EIZZ. So that is the very important equations, and as a result of beam theory. So so let's say we have a beam length L under bending moment M, and then this one will the cross sections. Okay, pay attention to each cross section will have a rotate. This will have a certain rotate and rotate and rotate. The angle will be larger and larger. So to achieve such a deformation is that is something like deformation is like that. So this one goes like that, and that goes like that, and that. As you can see here, the theta angle, this is the theta angle. The theta is gradually increasing over the along the length. This is x. So this deformation tells us that the shape will be like that. So again, the theta dx is given as the moment, which is the moment we apply, and then E is the Young's modulus of this material, and IZZ is the very important cross-sectional property, which is the moment of inertia. So d theta dx equal m E ZZ. Now, say this is the length L, and this one is the final angle of rotations. Let's say phi 0 and theta 0. Sorry. Then this one we can say theta 0 over the L. Okay, so final the theta 0, we can say that moment times L and EIZZ. Okay, that is the angle of rotation on the moment of the beam of length L and Young's modulus E and moment of inertia IZZ. So this is the final equation, very important. Okay, and then let's try to calculate stresses. Remember, we had a stress, which one is in terms of epsilon xx, and epsilon xx was is like that, but this time the d theta dx was the unknown, but now d theta dx is a known, which is the, now we can say moment divided e times I. So we put it back and then we calculate the sigma xx. That is the subject. So again, I will summarize here. The curvature, okay, the curvature 1 over r now is a dx, d theta dx is given in terms of a moment and cross-sectional property E and Iz, and stress strain is the these relations. And then deformation condition, we already consider that in derivation here. Importantly, the bending stress was like that simply, and epsilon xx is the y times d theta dx. It's nothing new. It's the same as before. We just repeat, and we just want to summarize again. And this one is simply like that. So if here, as you can see, this Young's modulus is disappear, and simply the moment, okay, moment and divide by the Izz and then y. So this is a stress distribution over the cross sections. Okay, this is a moment where the this is the moment applied to these cross sections, and Izz is the moment of inertia, and simply Izz is the integrations of dA, and then proportional to y, and by definition there is a minus y. Y means that the plus upper we have compressions, and minus y we have a tension. Okay, so that is the final sigma xx. Here I want to emphasize, as you probably have noticed, that this stress, and this is the shear stress in a shaft under torsions, and this shear stress is simply calculate T is a torque applied to cross sections, and IP is a polar moment of inertia and proportional to R. It is like a force divided by cross section property and proportional to R. And the sigma xx on the bending is very similar. And this moment is a force, and I is the cross sectional property, in this case a moment of inertia, and y is proportional to y, and there is a simply a minus because upper is a compression and down is the tension. Okay, so this is very similar to a torsion case. And there is one very important issue, is that this neutral axis. You know, in the very beginning, we just assumed that this is the y equals 0, and this is called the neutral axis. But we didn't say where. We just use the y equals 0, but we need to know where this neutral axis located. All the strain, all the stresses, as you can see here, at the 0 at a neutral surface. So we need to know where this neutral axis located. In other words, where is a y equals 0? Okay, it's very easy and straightforward to determine this one using one condition, that net axial force should vanish. What does it mean? We have all the stresses like that. Okay, we have this is a tension, and this is a compression, and this gives us a moment. But all the sigma xx should not give any fx forces. Fx should not be any value, this should be a 0. So simply fx is the integrations of a sigma x over the dA, and this is the fx, and then this sigma x is simply we already know this is the Young's modulus and this is a strain, and this Young's modulus and this R is the out of the integrations. And then what is left is the integration y dA equals 0. Okay, so this location of y has to meet this condition. But what does it mean? Integration over y dA equals 0? Well, that means, okay, this means is that simply the definition of the center line. So center line or centroid. So this one is simply YC times A is the location of the centroid of the cross sections A, and which has to be 0. So simply YC equals 0. What does it mean? This neutral axis should go through passing through the centroid. Okay, so if this one is the cross sections rectangular, this axis, this neutral axis, always the centroid, which means that this one and that is the same one. And if the cross section is the triangle, then the neutral axis locate to this one is the 2-to-1 ratio. So this is the neutral axis, and simply as you can see here, this is the minus and this is a plus, and this is a minus and this is a plus, and the sum of these forces should be 0. So it's clear that y, the neutral axis, should be passing through the centroid. Again, the sigma x, the summation of a sigma x should be 0. That's the reason why we have a neutral axis should pass through a centroid. Okay. Now, a very important point is that we want to compare all the theory we have studied: bar and shaft and beam. A beam we just studied, and the load for each case, as you can see that the bar, the force is the simply axial force, and the shaft is simply the twisting moment, and beam is the bending moment. Okay, that is the load for each case. And the cross-sectional property, as we observed in studying the bar and shaft, this bar, the cross-section is simply cross-section and integration dA. The shaft is the cross-sectional property is simply polar moment of inertia. And now beam, in the case of a beam, the cross-sectional property is the moment of inertia, integration y square dA. And stress is a bar force divided by A, and shaft, this is the force and this is the cross-section, this, and then proportional to R. Very similar to this case, the beam sigma x is the moment and cross-sectional property, in this case IZZ, and then Y. And the strain is like this, and gamma and epsilon, and deformations is very similar in the theta and this, and the material property is the Young's modulus and Young's modulus, because the beam is a series of the tension and the shaft is a series of shear deformations. Okay, so the we can summarize here, and this is the a flow chart for the bar. For the bar, this red color shows the bar, and this green shows the shaft. Now have a beam. We have a beam like that, and so the moment will be sigma x and y. This is a y, and dA, and this is a sigma x for the stress, and stiffness is a E, and strain is a simply epsilon x, and that is the given as the minus y over r, or minus equal minus y times d theta dx, and ux is the simply x times y times there's a minus dx d theta dx. So as you can see that there is a very very close the identity, the analogy between the bar and the shaft and beam. So that was the summarized here, and very clear. And this table will help us to understand three structures: bar and shaft and beam. But the most important case in the bar in the beam is that the cross section now is the moment of inertia. Moment of inertia. Okay, so let's have a 10-minute break.